Welcome to Lecture 1 of Networks, Friends, Money, and Bytes. And today we'll try to formulate and answer the question about our smartphones, especially on 3G, the third generation cellular network, which all use some ingredients of the so-called CDMA technology. So what makes CDMA work for my smartphone? And this lecture video is divided into 5 modules. Take a look at your smartphone, which could be an iPhone, an Android phone, a Windows phone, and you see that it is a symbol of our age of connected lives. It symbolizes a lot of advances. For example, advances in networking technology and services, including wireless networks, the internet, the web, which together with many other technological advances has provided this wonderful device we're holding in our hands today, such as chip design, touchscreen material, battery packaging, software system, business models, and so on. Now we can't help but marvel at this wonderful device. It has become the smart and mobile center of our network lives. And we use it not just for voice communications, not just for making phone calls, but also for what we call data applications, which could be email, web browsing, streaming video, video conferencing, uploading photos, downloading files. And these data applications' performance could be measured, for example, in the unit of bits per second. Now we'll be focusing naturally on the networking dimension of smartphones. And it traverses actually a few different networks. First of all, the radio air interface between your device and, for example, the base station of cellular networks. That's the focus of today's lecture. And then it goes through what's called a cellular core network, which is a wireline, a landline network. And these two together form the cellular network. And then we'll traverse the backhaul of public internet, an IP network, before it reaches, for example, Google's data center that houses the YouTube server, which you might be watching this video from at this very moment. Now, if we look at the cellular network, that part of this story, we see that terrestrial wireless communications dates back to at least 1940s. And since the 70s of the last century, we have seen the growth of cellular networks. From the first generation analog communication to second generation digital communication in the 90s, bridging through 2.5G to the third generation, heavily focusing on data application in the last decade, and now to what people call the fourth generation, okay, one of which is called the long-term evolution LTE networks that's being rolled out in America as well as in certain countries in Europe and Asia. Over the next few years, we can anticipate a lot of LTE deployments. Okay. Now, back in the 1980s, some estimate that there will never be more than 1 million cellular users in the US by year 2000. It turns out this was one of those way off underestimates of the proliferation and impact of networking technologies. Later in lecture 18, we will talk about a different kind of wireless networks we also use a lot, the Wi-Fi networks. They started in the late 90s and continues to today. So today's focus is cellular network. And what is a cellular network? Why do we call that cellular? What is a cell? Now I have to first understand that the air interface of a cellular network or Wi-Fi networks use parts of the electromagnetic spectrum. For example, in Europe, the most popular second generation cellular network was called GSM, and the frequency band around 900 megahertz was devoted to GSM. And one of the popular third generation networks was called UMTS, whatever that means. We're not going to be bothered with the acronyms too much today. 1.95 to 2.15 gigahertz part of the spectrum was devoted to UMTS. And these are the so-called licensed band, meaning that you have to pay government a lot of money in order to have the right to transmit. And for example, in the US, the government has collected tens of billions of dollars from wireless operators and sell them the right to transmit in different regions of the country in different parts of the spectrum. Suppose you are given a certain part of the spectrum, for example, between 1.95 to 2.15 gigahertz. You can divide that further into different chunks of frequency bands. And usually, these frequency bands are used in the following way in cellular network. You see the entire space is divided in this idealized picture into many hexagons. Each of these is called a cell. And in the cell, there's an infrastructure called the base station, sometimes called node B in 3G or evolvable eNode B in 4G. And then there are also many mobile stations, MS, sometimes called user equipment. And each base station is usually composed of directional antennas pointing to different directions. For example, 3 sectors, each being 120 degrees, with a set of direction antenna pointing towards that direction. And we call the communication from the base station to the mobile station downlink. And from the mobile station to the base station, uplink. And we're just not drawing the other parts of the cellular network. How do we connect these base stations to the rest of the internet? That will be for later lectures. So today we just focus on the air interface. And you may wonder, why do I divide the space into hexagons? That has to do with the way we're using the electromagnetic spectrum. Let's say one big chunk of this overall frequency band is labeled 1, another labeled 2, 3, 4, 5, and so on. If I use the frequency band labeled 1 at this physical location, what happens is that signals would attenuate over distance. Suppose the distance between this base station and this mobile station is d. And the signal attenuation drops over distance, roughly speaking proportional to d to the power minus 2 to d to the power minus 4. Depends on the propagation environment. Now, this sounds like a bad news because your signal gets weaker and weaker over distance. In fact, it is a blessing. Because of this attenuation, I can reuse the same frequency band, labeled 1, at a sufficiently far away distance. Okay, and this is what people call frequency reuse. So I will just tessellate these cells, hexagons, in the space, and then I'll be able to reuse the frequency as long as they are far apart enough from each other. Now, in this case, we see a frequency reuse factor of 7. So this was the essential idea, leveraging the fact that signals attenuate over space to reuse the same frequency band. Now, imagine how inefficient radio communication would be if you cannot reuse frequency band. Then if you have to cover 100 regions, then you're going to need 100 of these chunks of frequency band. And you soon run out of the spectrum to use. Now let's take a closer look at this resource. The resource is the air. or more precisely, the spectrum. We talked about a licensed spectrum. There are also unlicensed spectrum, which forms the foundation, the media, for Wi-Fi communication. Over there, you do not have to pay anyone to get a right to transmit. As you can imagine, the jamming situation can get quite bad over there. Now, we'll worry about that in Lecture 18 on Wi-Fi. In the air, the signals suffers all kinds of distortion. One is signal attenuation. Okay. The power drops over distance, and that leads to frequency reuse and the foundation of cellular network. Another feature is interference. Okay. Not only you are transmitting in the air, other people are also using the air, and you might collide. Later in Lecture 18, we will draw a detailed picture of what actually happens during collision of packets. Today, suffices to say that if two users transmit at the same slot in time, then their signals will interfere with each other. And the analogy that we'll focus on in today's lecture is a cocktail party analogy. So suppose you are in a cocktail party and you want to talk to your intended recipient. Okay, so Alice wants to talk to Bob. Now there are many other people around you, and they all talk to each other. For example, Chris may talk to Dave. And so happens that you are very close to Chris, and therefore Chris' voice actually becomes interference to you. And then there are other people around the intended recipient, and their communication also interfere with your conversation. So Bob will actually hear a lot of different voices overlapping on top of each other. Now the question is, how can you communicate in such a cocktail party? How can you mitigate and manage the challenge of interference? Now, one strategy that we'll be focusing on in today's lecture is transmit power control, or in the case of cocktail party, volume control. You're going to try to install a protocol of courtesy that says, if you don't need to shout, please don't. And that is the spirit of transmit power control in 3G CDMA network that we'll be talking about momentarily. So keep this cocktail party in mind throughout today's lecture. Now, resource allocation is a key theme that will be recurring throughout the course. In today's lecture, we will see two different philosophies of allocating resources. Now, the resource could be time, it could be frequency bands. In orthogonal resource allocation, it says that I'm going to chop up one of these axes, say time, and then give different users different slots. For example, Alice talk, now Bob talk, now Alice talk, now Bob talk. So no two people will actually talk at the same time. Now, clearly this is hard to implement in a large cocktail, but in certain technological networks that is feasible. Or I can chop up the frequency dimension into different frequency subbands and say, Alice take this subband, Bob take this subband, and so on. Now this is called orthogonal resource allocation, either time division multiple access or frequency division multiple access. There's actually another dimension of resource. It's called code. Now, we're not going to the details of signal processing or communication theory, but roughly speaking, it says that you're going to send the digital information in bits, right? 0, 1, 1, 0, 0, 1, 1, 1, like that. Okay. And what I'll be doing is to multiply your digital information on a much faster scale with a sequence of ones and minus ones. What's called a code. And these code will scramble your transmission almost into a noise-like, a random number-like sequence. And only the intended recipient will have the right code to decode that message. And the other receivers would not have the right code. And therefore, they would not be able to decode your message. In a cocktail party analogy, this is like different languages. Okay. So if somebody is talking Spanish and another person is talking Korean, that will help to differentiate the conversation. Now, of course, it is only an orthogonal resource allocation if these codes are ideal, in the sense that they can perfectly differentiate the conversation. Just like in languages, sometimes the same pronunciation are valid in different languages. They just may have different meanings in different languages. In practical CDMA, it's actually non-orthogonal. There will be interference still. For example, in the uplink, different mobile stations have different clocks. In the downlink, there still might be channel distortion and shifts the signal. So in any case, a practical code division multiple access CDMA is non-orthogonal. Okay. You are effectively sharing a common resource in the air among interfering users. This doesn't sound like a very attractive idea at the beginning, but as history showed, it turned into an extremely successful technology. It started by a company called Qualcomm, which has since become one of the pioneers of many wireless technology innovation. And that was back in the late 80s. And then after quite a few years of debates in the 90s, it finally got standardized as so-called ICE95 as one of the 2G standards, and got very popular in US for certain operators and in certain parts of Asia. And then in third generation, both main tracks of 3G, one is called UMTS, the other is called CDMA 2000, actually use elements of CDMA technology. Okay. So if you're using a 3G phone, then you are using CDMA.